regular physics class. I hope that you're ready to have a good afternoon heading into your weekend and ready to learn the rest of this section, moving ourselves forward, getting you where you need to be. So hopefully my favorite student, which one of you is that? No, can't have favorites. I do love you all, and I'm hoping that that pancake breakfast goes amazing for you, and that you earn plenty of money for your missions trip. And so enjoy your weekend, and hopefully you'll be able to do some of these physics problems as you get ready. Your due date's on the sideboard, as you know. So let's just make sure that you're prepared for that. Yesterday, we learned about the first of our position when acceleration is constant equations. Now we have several of them. And the reason we have several of them is because sometimes you have different given information. In this case, this is when you know that you have constant acceleration, but you don't know how much the constant acceleration is. So you won't even necessarily have the graph, but this is going to be a great equation. We had ended on this last time. It's the starting position plus the displacement, or how far it went. When we ended the class, I told you to write this down, but just in case you missed it, the final position equals the initial position plus 1/2 of the initial velocity plus the final velocity times the time, or how long it took. All right. So based off of a VT graph, it's used for solving problems even when we don't make the graph. So we need to look at an example of that in a little while. There is another equation that also lets you calculate the position when the acceleration is constant. This one looks suspiciously as if it's a quadratic equation, which it is. I'm not showing you where it came from, but I want to talk through what it does for you. Once again, it's a position at an instant or at a specific time. It equals the starting position plus a couple of different things regarding the change in position. So starting position plus starting velocity times the time plus 1/2 of that constant acceleration times t squared. We can label that. So take a second to label it. Final position equals initial position plus initial velocity times the time plus 1/2 at squared. This is also the time. This is actually the equation that, in my mind, for whatever reason, if I had to memorize them, that's the one that sticks for me. This equation is also based off of a DT graph, but it's when you have that parabolic shape, okay? This one was based off of a VT graph. We will not be necessarily pulling it from the parabola or from the quadratic equation, but we once again will be able to use this when we don't have a graph, but I want to relate that to a graph. So what these look like in their graph forms, okay, this equation came from this idea where you have constant acceleration on a VT graph. A parabola on a DT graph also indicates constant acceleration. Okay, these two mean the same thing is happening. This one shows where it starts. This graph does not show where it starts. So in a problem using this idea, you would have to be given the initial position somewhere else. Okay, don't worry, we'll get to some concrete examples soon. And there's one more equation that deals with position and it deals with constant acceleration. And we need to have all of these three equations at our disposal in order to pick the one that's going to best fit the problem. Okay, so this one deals with if we don't know how much time it took, but we know both the starting velocity, we know the ending velocity, we know the acceleration, starting position and ending position. So this one can also be used to solve word problems. And here's our labels. Final velocity squared is initial velocity squared plus 2a times d minus d0. So to consolidate these, and it's always good when you start doing problems to have a list of the equations handy. So most of these slides down here are just blank for whatever reason. Here's my handy dandy list of equations. I'm going to just copy them and paste them in as we start looking at that individual sheet. Remember, I had given you a sheet that was labeled 5-3 acceleration, but then I gave you a sheet that had a couple of problems right along with. Here's this one that says a car starts at rest and speeds up at 3.5 meters per second. So I'm going to put our equations here. We're just going to use those. So I'm going to put that here and move this out of the way. And then I'm going to go back here and I want to pull this equation because I don't want to just reveal it. I would like for you to be able to see what's happening on this. I'm going to copy and I'm going to paste. So the car starts at rest and it speeds up at 3.5 meters per second squared after the signal turns green. And we want to know how far it went when it's going 25 meters per second. So I want to identify what's happening here. I want to go back to drawing a little picture so we can have this in our mind. Okay, this is why we did chapter 3, by the way. So you've got your car. It is sitting. This is 0, and this is our direction for positive. Direction for positive, super important because we need to be doing positives and negatives as we go. There's nothing changing about the acceleration. It starts, light turns green, off it goes. The acceleration is constant at 3.5 meters per second per second. The velocity, however, is not constant. The acceleration is constant. So the velocity is doing this. Okay. And our acceleration is doing this. At the beginning, we set our stopwatch at 0. At the end, yes, I know we used 1s and 2s before, but we can use 0s and 1s here to help us to navigate this. Our later time, we don't know how much time it took. We know that our starting position is at 0 meters. And our ending position, or our later position, once again, we don't know what that is. However, how far will it have gone? We've just identified right here, this is the thing we're trying to find. We're trying to find the later position. Okay, so let's kind of indicate that here. Our velocity. We know our starting velocity is, okay, well, it starts at rest, so we have 0 meters per second. We actually know our last velocity. We know our ending, our later velocity. Our later velocity is 25 meters per second. From our drawing here, we can remind ourselves that it is in the positive direction, so we're good here. And the acceleration for the whole thing is 3.5 meters per second squared, found right here. Okay, so let's think about what we have and which one of these equations is going to make sense. Okay, we're trying to find D. Okay, so our later D is actually going to be the D without a subscript. So out of these 3 equations, I have to rule out this one. I rule out this one because this is when acceleration is 0. Acceleration isn't 0, so we can't use this one. V equals V0 plus AT. Well, that's great, but we're asking for how far it's gone, so we're probably going to rule that one out. So then you look at the other ones and see if you have enough information. This one needs a D0, which I have. It needs a V0, which I have. It needs an ending V, which I have, and it needs a time, but I don't have an ending time, so I'm going to X that one out. This one needs a D0, which I have, needs a V0, yep, also needs a time. So let's focus in on this equation. This V is our later V, so we have that number. I have 25 meters per second squared. The starting velocity is 0. The acceleration is 3.5. Our ending position is what we're asked to find, and our beginning position is 0. Now, hopefully you're starting to see why we like to have 0 at the beginning of our problem, because usually when you plug it into an equation, we're going to have a lot of things drop out. Okay, so 0 squared is 0, 25 squared is 625. 2 times 3.5 is 7. D minus 0 is D. So I'm left with something very nice and simple, and that would be to take 625 divided by 7. Okay, so 625 divided by 7. So we have about 89.3. And since it's meters per second squared and meters per second, our position is going to be at 89.3 meters. That's also how far it will have gone because we started at 0. So 89.3 meters would be our answer for that problem. Okay, so here once again, I've got that all mapped out. There's our car 1 and our car 2, our organized information, 89.3. Okay, continuing on to the next problem on your list. This might look suspiciously like what we had done before. Okay, but we had only done the setup before because we didn't know how to solve it. So I want to go back to our pictures again, and we want to consider what's happening here. Car is going 25 meters per second. The driver sees a child suddenly run in the road. It takes the driver's 0.45 seconds to hit the brakes. As it slows, the car has a steady acceleration of 8.5 meters per second squared. Actually, it should say of negative 8.5 meters per second squared because they're slowing down. What's the total distance the car moves before it stops? So let's take a look at this scenario. So we have two things happening. We have the car moving right along, okay, and we're going to let 0 be here and positive this direction. And during that first 0.45 seconds, it's continuing to just move along at that constant speed. Okay, so here's our location 1, here's our location 2. So we have, here's our constant speed happening. Okay, there we go. Then they hit the brakes. So after they hit the brakes, it continues to move, but this is where it is going to get ready to stop. The velocity now is getting slower because they're hitting the brakes. Okay, this is always hard to Okay, so it's getting slower and slower until it reaches a stop. So these are also velocity vectors. The acceleration over here is 0. The acceleration here is in this direction. So when we're organizing our information, we need to think of it in two phases. We need to think of it as far as how far the car moved here, and then how far the car continued to move and put it all together. So we have really two phases of this, but let's organize the information. This first time is 0 seconds on the stopwatch. Second time is 0.45. So we know that it took that long. And then our third time is unknown. We don't know how long that took. We know our first position, where we start, is at 0 meters because we were smart about where we picked. Our second position, we don't know. And our third position, we also do not know. What we do know, we know that we have a starting velocity of 25 meters per second moving forward. At V2, think it through before I write it. At V2, how fast is it going? I hope you thought 25 meters per second. It hasn't slowed down yet. By the end, our ending velocity, though, what is the total distance the car moves before it stops? Yesterday we said stops means 0 meters per second. Then we have two phases. We have the acceleration at the beginning from 1 to 2, and that is 0. And we have the second phase from 2 to 3, where the acceleration is at negative 8.5 meters per second squared. Okay, great. So now what do we do with that? Like I said, we have to consider this problem in two phases. In the first phase, the car is still moving. It moves a certain distance. In the second phase, it's also moving. So we're going to break this down and we're going to look at the first part first. Okay. In this case, acceleration is 0. So in this particular part, it is okay to use this equation. This is the dangerous one. You have to be sure that acceleration is 0 or you can't use it. So we're going to say here that for this first phase of what's happening, d equals starting position, which is 0, plus the velocity, which is 25, times the time, which is 0.45. So in the beginning, phase 1 of this problem, whoops, that's a little too small. In phase 1 of this problem, we have 25 times 0.25. No, 0.45. 0.45 seconds, which 11.25. So the position so far where it went to is 11.25. So that's our how far we moved from here to here was 11.25 meters. Then we need to consider phase 2 of the problem. Okay, if you're having trouble seeing that, let's put it back up to full size real quick. Okay, once again, for phase 1, we have from here to here, and we needed to figure out it went 11.25 meters per second. Phase 2 of the problem, we're considering our time no longer starting at 0, and we don't know how much time. We actually now have a bit more information as far as where it started. If we'll notice, 11.25 meters is right here where the car is now. So we can now get rid of this question mark and say that it's at 11.25 meters here. And we're trying to figure out where it is at the end of its motion. So if we use this part, we are actually going to find the position where it is at the end, because it's starting at 11.25 and moving forward from there. For this phase of the problem, the acceleration is no longer 0, so we cannot use this problem for this phase of the we can't use this expression for this phase of the problem. So nope. We're trying to look for something that's going to help us find the position. So one of these with the information we have. We don't know about how long that's going to take. But we do know two velocities, and we do know an acceleration, and we do know a starting location for this phase. So once again, we can use this equation. I can say v squared, this is our ending velocity for this phase. So I can do 0 squared equals starting velocity 25 squared plus 2 times negative 8.5. This is why it's important for us to have the negative going against. Our picture helps us with that. Ending position is what we're trying to find, minus starting position, which is 11.25. We're not starting all the way back here because we had to figure out how far it went to get to that, but this is going to give us our final answer. So here we go. We have 0 equals 625 minus 17 times d minus 11.25. Let's distribute. So we're going to take 17 times 11.25. Let's finish with the algebra. I know you're all capable of that, so I'll just do it kind of quickly. So we get about 48 meters. And that is our final answer, the 48 meters. Because we already started at the 11.25 and we went forward from there. And that wraps it up for section 3. You guys are now free to work on your assignments until the end of the period. Next up, when we get back on Monday, we'll be delving into section 4, wrapping up the chapter. And so I hope that you have a great weekend. Please make sure that you are working towards the goal, knowing when your deadlines are, so that you can do a fantastic job and not be overstressed and leave too much to do at the last minute. Okay, God bless you. Have a great weekend. Bye.